Okay, welcome back. Let's unpack something interesting today. What if I told you there's maybe a surprising link between, say, calculus class and, well, your refrigerator?
Yeah, it does sound a bit strange at first, doesn't it? But
Mhm.
it's definitely a real thing. We've been looking through some, source material notes, bits of research, and it really digs into how math, specifically calculus, gets used in something super practical like food science,
Yeah.
especially for understanding how bacteria grow in food.
Right, I saw that. These sources, they sort of lay out the basic calculus ideas first, and then bang, they pivot to this really cool application using these math tools to look at bacteria. So I think our mission for this deep dive is pretty clear. Really get how integration helps figure out the total bacteria count
Hmm.
over time.
Exactly. And that's key for anyone who's maybe wrestling with differentiation right now.
Yeah.
Measuring rates of change, how fast things happen now, and then integration, which is more about adding things up, accumulating those changes over a while. Well, this gives a solid answer to that why learn this question. It's abstract math describing something real, something that changes over time.
Okay, so we're connecting the dots then. How do you jump from knowing the bacteria's growth rate, which that changes, right?
Yeah.
Based on temperature time, to knowing the actual total population, the amount that's built up in that leftover container in the back of the fridge?
And that total number, that's what's really critical in food science. It's the difference between food being safe and, well, spoiling
But yeah.
or even a health risk. See, the growth rate isn't steady. It often speeds up as the numbers increase if conditions are right. So just knowing the rate at one point doesn't tell you the whole story, the scale of what's happened over hours or days.
Okay, yeah, that makes sense. So if that rate keeps changing, how does calculus actually capture the overall buildup? It can't be as simple as just like rate times time, can it?
No, exactly right.
Yeah.
Think about it like driving. Differentiation is like checking your speedometer. That's your speed right now, instantaneous rate. Integration, though, that's like using all those different speed readings to figure out the total distance you covered on your whole trip.
Bacterial growth is kind of similar. The rate changes, but for food safety, you need the cumulative distance, the total number of bacteria that have piled up.
Okay, got it. So integration is the tool. It adds up all those tiny fluctuating increases in the bacteria population
Mm.
from when it started right up to whenever you measure it. Gives you that crucial total. It lets scientists basically calculate the whole history of the growth. That's exactly it. You integrate the function that describes the growth rate over a certain time period, and that quantifies the total bacterial load that's accumulated.
Mm.
It's incredibly useful because these growth models often use, like, exponential functions. Integration finds the area under that curve, mathematically speaking, which represents the total count.
Okay, so knowing that total count is super important. How do food scientists actually use this number once they've calculated it? Like, what decisions come out of this math?
Yeah, this is where it hits the real world. Knowing that predicted total load over time, it lets them do a few key things. One, set those best by or expiration dates. They calculate when the total count is likely to hit an unsafe level under typical storage. Two, create safe handling rules. Like if food sits out at room temp, the growth speeds way up. Integration helps predict how fast that total hits dangerous levels. That informs things like the 2-hour rule.
Right, I've heard of that.
And three, develop standards for processing and storage, figuring out the best fridge temperatures or cooking temps. It all comes back to understanding how these factors affect the growth rate and therefore the total accumulation over time.
Wow. So it's really not just some theoretical math problem. It's directly tied to keeping people from getting sick and maybe even cutting down on food waste by predicting spoilage better. It makes integration feel much more practical, a protective tool.
Precisely. It's a great example showing that math isn't just stuck in books. It's fundamental for modeling and understanding these dynamic, cumulative processes happening all around us.
Hmm.
Microbes, ecosystems, maybe even economies.
So wrapping this up then, what this means for you listening is that this tool, integration, it's being used constantly in labs to help make sure your food is safe. And maybe something to think about, if integration helps calculate this total bacterial buildup from a changing rate, where else could that apply? What other cumulative things do you see in biology, maybe economics, even, I don't know, personal habits, things where understanding the total change calculated from a rate could give you new insights? Maybe calculus is sort of a hidden language connecting all these different areas, something to chew on.